So now let's move on to the upper extremity prosthesis, which is the Smart Hand Transradial Prosthesis. So let's move on to the background. So the hand is a powerful tool, and its loss causes a severe psychological and physical drawback. Despite significant impact of losing a hand, there's not enough amputees to push manufacturers to innovate their products, so that both control interfaces and mechanisms have barely changed in the past 40 years. The development of a more functional and naturally controlled prosthetic hand has been an active research in the field for decades and is still one of the biggest research challenges in rehabilitation. The is to design and develop a new, lightweight, dexterous, and sensorized prosthetic hand with an intrinsic actuation, transradial prosthetic hand able to be fitted in subjects with an amputation level long below the elbow. This hand is meant to be clinically experimented by amputees employing different levels of interfaces in order to investigate the effectiveness of a more natural and initiative control and feedback strategies. The smart hand could be experimentally fitted on transradial amputees. For the requirements and design principles, the hand cannot be conceived to reproduce its human model, where the hand is a non-separable part of the arm, deeply integrated with it, but must be considered like an independent, modular, self-contained end effector. This smart hand should allow amputees to achieve power grasp used in approximately 35% of ADLs, precision grasp, lateral grasp, index pointing, which is useful for pressing buttons, and basic gestures, which is useful for when the patient is counting. Biologically, the prosthesis should attempt to compare with the human hand in terms of anthropomorphism, with a size and weight of about 400 grams, number and distribution of independently actuated degree of freedom, static and dynamic biomimetism, sensorization, and performance, with the speed of the whole hand closing in less than 2 seconds and grasping force able to stably handle everyday objects. This is a smart hand architecture. The hand sensory system is designed to be used both for the automatic control of the grasp and for delivering sensory information to the user. Let's move on to the supporting skeleton. All components of the hand are housed inside a supporting skeleton machined in an ergal alloy aluminum. The base of the skeleton integrates a standard myoprosthesis wrist adapter. The smart hand control board is placed on motors and covered by a plain carbon fiber plate acting as the palm of the hand. For the flexible controller and communication, the architecture is flexible enough to support real-time control of the four active axes, real-time identification of external commands, computation of control loops, and delivering sensory biofeedbacks.
So the weight of this prosthesis is close to the natural hand weight. The standard wrist attachment and batteries are not included in the weight measurement. Comprehensive list of measured features include finger dynamics, speed, grasping capabilities, grasping forces, degree of adaptability, supporting grasp capabilities, and power consumption. As you can see in the picture, the left column is a smart hand with silicone tubes on the fingers in the three basic prehensile patterns: power, precision, and lateral grasp. On the right column, as you can see, that is the smart hand in comparison with the commercial prosthesis. Those are the grasping capabilities of the smart hand prosthesis. Next is the grasping mechanism. These are actually pictures from a video sequence of the middle ring and little fingers wrapping around the cone, showing the degree of adaptability of adaptive grasping mechanism. In the top row, the little finger is the first finger that touches the object, whereas in the lower row, the little finger is the last one. So this is just the transradial prosthesis design. A smart hand prosthesis is a 5-fingered, self-contained robotic hand with 16 degrees of freedom, actuated by 4 motors, implementing automatic grasp control, and has potential delivery of sensory feedback to the amputee. It also weighs 530 grams with a speed of closing time 1.5 seconds and can lift a 10-kilogram suitcase. It stably grasps up to 3.6 kilograms of cylindrical objects too. As per the advancement in this prosthesis, the prosthetic training will be much longer since it has many controls. But when the patient has mastered controlling the smart hand prosthesis, the patient can now participate in functional activities and regain the function of the hand better than any other prosthesis. This is costly and of course high maintenance, but this will really be life-changing once proper training of prosthesis is achieved. Here, most goals are met.
Now let us proceed to the feet prosthesis innovations. Proprio-foot with the use of microprocessors and sensors has been discovered or introduced for over a decade, which functions to provide power dorsiflexion of the foot. Its motion, on the other hand, is an upward rotation of the ankle that raises the toe, which is the action that effectively increases the ground clearance of the foot as it swings through the air. Prior to proprio-foot's existence, the use of microprocessors seemed to stall. Because according to several numbers of researches, the use of hydraulics seemed to be more beneficial to increase the ability of the foot and ankle to adapt to uneven surfaces in real-world environments. Subsequently, microprocessors were still incorporated or included with the use of hydraulics to provide reactive adjustments to the hydraulic resistance to motion of the foot and ankle. Due to this mechanism, it increases the foot and ankle units' responsiveness to changes in speed and an uneven terrain beyond that provided only through resistance to flow. On the other hand, microprocessors are also being used to send output signals to motors. Now let us proceed to the prosthetic feet, which is also running into some advancements in areas such as materials and geometry. An example of this is Rush Feet, which is made of fiberglass originally designed for Apache helicopters. The fiberglass material, on the other hand, is an alternative to the near standard of care carbon fiber material. The fiberglass material seems to decrease hysteresis as the foot cycles through a sequence of steps. With regards to geometry, the ProFlex developed by Osur engages a series of levers as the foot progresses forward from the moment it contacts the ground to later instance while shifting the ankle's rotation point. On the other hand, it is also intended to accommodate a relatively active user, one who enjoys hiking and jogging as well as level ground walking. It comes with an aesthetically pleasing anatomical foot cover and integrated male pyramid. Now let us proceed with the knee prosthesis innovations. So it has been more than 15 years since a microprocessor was used to assist with control of a prosthetic knee joint. Recent advances in sensor technologies and algorithm improvements have greatly enhanced this technology. The Genium, which uses a combination of accelerometers, gyroscopes, and strain gauge to calculate knee angle, the lower limb position relative to the environment, and the moments at the knee and ankle. Servomotor, on the other hand, is controlled by the Genium, which opens and closes valve points on hydraulic cylinders to reduce or increase the knee's resistance to flexion and extension. The control algorithms, on the other hand, now learn and optimize the activity based on the user's walking patterns, such as artificial intelligence at work. By being able to appropriately sense the knee's position and being programmed to learn the proper response to maximum user's function and safety, microprocessor controlled knees can effectively increase users' range of walking speeds, reduce the incidence of falls, and improve the user's ability to participate in a range of activities. In addition, microprocessor-controlled knees are now manufactured with increased resistance to the elements, including several waterproof models, and a few others with weatherproof ratings. On the left side, as you can see, this is a biome ankle, which is an example of a knee prosthesis. And on the right is a ProFlex XC by Osur, which is under the feet prosthesis.
So for socket technologies, first off, the socket is the connection between the living biological system and the artificial prosthesis. One of the innovations that have been made to improve the socket is called the Comfort Flex socket. So it's over here. And this is a modern socket design that isolate muscle groups, and they are a more anatomically correct design than previous sockets for users with above-knee amputation. RevoLimb, this one over here, is a marketed boa closure system that lets users tighten and loosen the socket according to the volume of their limb. This is added to the sockets of the above-knee amputation patients. RevoLimb also lessens the need to carry around prosthetic limb socks used to restore fit. We move on to the protective interface. This is applied between the user's residual limb and the rigid socket. This helps prosthesis users obtain a comfortable fit. They are constructed from various silicones, thermoplastic elastomers, or urethanes. One of its cons is that it insulates the residual limb, thus creating a hot and uncomfortable environment. So the innovation that has been made for the protective interface is a new silicone liner with Outlast technology. This is a material that uses phase changes to capture and retain heat, which aids in cooling the user's residual limb. It also provides increased comfort for individuals using prosthesis, leading to increased activity. So the liner over here is embedded with Outlast technology. For the instrumentation innovations, we have what they call Europa Plus. This is an instrumentation development that attaches the prosthesis to provide moment data at the connection point just below the socket. Over here is the Europa Plus attached below the socket. This information can be read and interpreted by the prosthetist to make changes to the positioning of the parts of the prosthesis attached to the socket, called alignment. It also minimizes stresses to the user's residual limb and mechanical stress to the parts of the prosthesis, thereby decreasing mechanical wear. The sensor of the Europa Plus can also record temporal symmetry in the user's walking pattern, a valuable tool that helps monitor the user's progress through rehabilitation.
Now let us proceed to the importance of physical therapists in prosthetics advancements. First, provides proper care for the residual limb to learn to recognize signs indicating incision from surgery is healing correctly or incorrectly. Aids in shaping of the residual limb by educating the patient to wrap the limb in such way to maintain the proper shape in order to don the prosthesis easily or correctly. Provides desensitization techniques to aid in sensitivity and phantom pain, thus helping the patient to be more comfortable before using the prosthesis. provides with regards on the use of orthotics with prosthesis, and lastly, educating the patient with regards to the proper fit and alignment of the prosthesis. By assisting with fitting so that prosthesis can function safely and help patient to function normally as possible to avoid overuse or dependence on the remaining whole limb.
We now present to you the last section of this presentation, which is the benefits of these innovations in physical therapy approach on amputation rehabilitation. So, these innovations provide easier facilitation of rehabilitation and patient management. They also improve ADL, or activities of daily living, and gait trainings. They also provide more customization options for the patient. They give both the physical therapist and the patient the opportunity to maximize the training sessions. They also enhance the physical therapist's knowledge regarding the advances of the prosthetics. And lastly, they improve the patient's quality of life.